I'm just going to quickly have a look at this spring question. It's the 2011 paper, and starting with question 16. Shouldn't be too hard, but I'll give you maybe 10 seconds to have a look and or 20 seconds to have a look and understand what's going on. Okay, so what's going on? Conducting experiment with a spring, it's suspended, it's 40 centimeters down. When the mass attached, without the mass attached, it's 40 centimeters. With the mass attached, the spring has a length of 70 centimeters. Okay, so it's stretched from 40 to 70. What is the spring constant K of the spring? So, we look at the forces here, and it's mg going down, and because it's a spring, we know kx is going up. Therefore, kx equals mg. Now, what are all these values? Mass of 1, gravity is 10, k equals 70 centimeters. Let me x equals 70 centimeters, but we do that in meters, because they're asking for it in meters down here. It becomes 0.7 k, or k equals 10 divided by 0.7. Okay, pretty easy. But that's not the crux of this question. The crux of this question is over this page where they give you a whole bunch of graphs. And what they're saying now is the spring is pulled down a further 10 centimeters from 70 to 80 and released so that it oscillates. And now the gravitational potential energy is measured. Okay, so what they're saying is we have our mass, we pulled it down, and now it's moving up and down. And here's a whole bunch of graphs. First question. Which of the graphs best show the variation of kinetic energy of the system plotted against the length of the stretched spring? So, we know kinetic energy equals half mv squared. Okay? And in terms of the potential energy, potential energy that changes linearly. So, like we just imagine this spring, this mass going up and down. Okay, it will stop at the bottom, move faster, slow down at the top, and then move faster, coming back down. Okay. So the kinetic energy is highest in the middle. It's proportional to a square, so it's not a straight line. Okay, and once it gets to it's pulled from 80 to 60, so it's 80 centimeters to 60 centimeters. At both ends, it's going to be 0. So we're looking for something that is 0 at both 60 and 80 and gets higher in the middle. Okay. So there's only really one here, so that would be D. Question 2. Which shows the variation of the total energy of the system of spring mass plotted against the length of the stretched spring? So this is going back to the idea of conservation of energy. So energy doesn't get lost. So whenever they ask total energy of the system, it always stays the same. Okay? So, we're looking for a straight line. It would be C. Which of the graphs best shows the variation of potential energy of the spring system measured from the lowest point, plotted against the length of the stretched spring? So, at 80, the potential energy of gravity, it's lowest to the ground. This is our 0 point. That's what they said. The energy is measured from the point at which the spring is released, 80. So it should go up as it goes up to 60. And we're looking for a straight line because it's plotted against the distance, like mgh, and this h is x. Okay? Equals our energy. So we're looking for something started at 0 at 80. So these two are candidates. Those aren't really. And we're looking for it to increase linearly until it reaches 60. So the answer would be B. So this one is B. And finally, which of the graphs best shows the variation of spring energy plotted against the length of the stretched spring? Give your reasons for choosing this answer for spring potential energy. So spring potential energy is half kx squared. Okay? Now, we know that its original point is 40. Okay? So like its original length is 40. And now we stretch it down to 80. And we're bringing it up to here, 60. That's what we're measuring from 60 to 80. Essentially, we know we have the most stretch at 80. So that's when it will be the highest, at 80. And finally, at 60, it will not be 0 because it's still stretched a bit. So it'll be a bit lower. So how do I put that? At 80, it'll be like this. At 60, it'll be like this. Finally, we know it's squared, so it's not going to be a straight curve. So essentially, it gets higher as you go further away because you're squaring the distance. So it'll look like this. So it should look like that. F. Okay, great. I hope that solves people's questions about this. And I'll try and explain the square thing one last time. Essentially, if you know it's squared, the closer it is to 40, the smaller it will be. Okay? Because when you square small numbers, they're small. But as you square bigger numbers, it becomes much and much more bigger. Because that's what a parabola looks like. Okay? And that's why it looks like that. Great. So I'll catch you guys later. Cheers.